Yes, if someone can confirm that I am audible and the screen is visible.
Sir, you are audible.
Okay, thank you. We start from the point where we left. So we are basically undergoing the detection or the decision theory, which is employed in digital communication in order to retrieve the information sent by source. So last time we discussed this error rate due to noise, and we finished up this whole derivation, I think. Let me check. Yeah, yes, we said that this is a binary symmetric channel. If at all, the P of 0, 1 is equal to P of 1, 0. This is the condition for it. This 0 and 1 may not have equal probabilities of appearing. It means that it may be the case that you have a binary symmetric channel with non-equal priors. Now, prior simply means the priori probabilities, which we introduced as P1 and P0. If they are equiprobable, then only 1 by 2. But for the definition of a binary symmetric channel, we only need P01 and P10. Okay, so if they are equal, then it is called as a BSC. Then we thought that why not express this error probability from an engineer's perspective, and it is in terms of the energy you put in and the error you get. Okay, because this is what a practical designer would try to see. So we expressed the error probability in terms of EB, and the ratio is EB by N naught is the quantity of interest, and I said that you may see figure 4.6 for the plot of PE versus EB by N naught. This curve is known as a waterfall curve, basically called as because it resembles a waterfall. Okay, so today we would start with the general theory. We hope to finish it by Friday, and then the last remaining 3 lectures next week we would study the modulation schemes. Okay, and that way we will close our course. Okay, so today is lecture 27. So let us see where are we. Okay, so we have done this. Okay. Okay. So the topic for today is detection theory for digital communication. Okay. So the point is that in the last lecture we saw that one is encoded into a signal which is, let us say, P of t, and my 0 is encoded in the form minus of P of t. Okay, where P of t is what? It is having a duration of dB and the amplitude is A. This is P of t versus t. Okay. Now here we are using TB because this is the bit interval. Now bit interval suits well because we have only one bit to transmit, either 1 or 0. Now if this is, you can say that this is a signal which is S1 of t. Let us say instead of using minus of P of t, I use a different version of P of t, that is P of t minus TB or anything. It means let us represent it by some S2t. Let us say this is your M1 and this is your message M2. Okay. So what your transmitter did was it mapped M1 to S1T and M2 to S2T. Now either of them goes into the channel. Channel is nothing but add W of t. This is the channel which we set, and at output you get some Y of t, which is equal to S of t plus W of t, Si, where I can be 1 or 2. Okay, S1T or S2T. So at the receiver, problem is to find out given yt is the index of m or the mi sent, or we can say to find out which SIT was transmitted. Okay, so this was the problem we studied. In that case, the problem we studied, we had only two choices, that is M1, M2. They were mapped to two waveforms, S1T and S2T. At the receiver, it needs to decide whether M1 was sent or M2 was sent. Now, what is the general framework for it? So now we will discuss the general framework. It means now you have the general framework. In the general framework, instead of being limited to only two possibilities, you will say you will have capital M possibilities. And for the capital M possibilities, you will have capital M waveforms. Now, this waveforms is what will really go on the channel. See, this M1 and M2 in the raw form they cannot go, because whatever hardware circuitry you will be using will be generating continuous time waveform. Okay, it needs to generate because everything is being generated through real elements, those elements which exist in nature. Okay, let us say oscillators and all these things which we have constructed. So they will be generating continuous time waveforms. So we need something in the continuous time which is in direct conjugation with the discrete data. So you can say that S1T directly is in one-to-one conjugation with M1. S2T is also with M2. It means given M2 you can uniquely find S2, and given S2 you can uniquely say that it was M2. Okay, this mapping you have decided as the transmitter. This mapping is needed so that you can modulate some continuous time signal through a continuous time signal and transmit. Okay. So the general framework. So in the general framework, you can say that the message source, emits one symbol every t seconds. Now the term has changed. Every t seconds, let us call this is symbol becomes and this becomes t. Why? Because if your set is containing only two, if there are only two possibilities, 1 and 0, then they can be called as bits or bit. Okay, you can call it at a bit, and the corresponding time as bit interval. And the corresponding time as bit interval. But when you have more than two choices, so with more than two choices, we call a symbol and the corresponding time as t or symbol interval. Okay. So this is quite straightforward, you can see. So there is no point of confusion that अभी तक तो ऊपर हम लोग टी भी बोल रहे थे यहाँ पे इसको, और इसको हम बिट इंटरवल बोल रहे थे या इसको हम बिट बोल रहे थे, बट अब हम लोगों ने टर्मिनोलॉजी चेंज कर लिया है कि सिंबल और टी आ गया. तो दिस चेंज ऑफ टर्मिनोलॉजी is not at all arbitrary. This is because we have more than two choices. Okay. So the symbol which is emitted, you can say, belongs to an alphabet of M symbols. Okay, there are alphabet of M symbols. Means there are finite. This is digital communication. So at the transmitter, the information will be countable, or you can say will be countably finite. You will have only a finite you can say messages to transmit in the case of digital communication. Okay, so you will have, what is this alphabet? It has these many, you can say these are the possible messages which you want to transmit. So you can take an example. For example, the quaternary PCM encoder. It means quaternary PCM encoder. It means it has four things. The 0 0 0 1 1 0 1. Now suppose you say that the what at the source it clubs the bits, or it does in the case of PCM, you can say the encoding is done using 2 bits. So if the encoding is done of the levels is done in 2 bits, so you will have 4 possibilities. So you can say M1, M2, M3, M4. You have possible 4 messages to transmit. Okay. And let, as we defined P of 0 and P1 in above case, we will define the probabilities also in the following case. So let P of 1, P of 2, comma, P of M specify the message a priori a priori probabilities. Okay, let us say that P1, P2, PM, they specify the message a priori probabilities. Now what the transmitter does it, so there is an MI. So at the transmitter, what it will do is it will assign a waveform to it. So SIT is the corresponding waveform which is assigned to a particular MI, and this mapping is known to both the transmitter and receiver. Okay, both will know it because this is what your transmitter and receiver are designed to do in a deterministic sense. The random thing comes from the noise only. Okay, this thing we know कि अगर MI आएगा तो हमें क्या भेजना है, और रिसीवर को पता है कि अगर SIT आएगा तो वो क्या ट्रांसमिट हुआ था, यानी MI. तो ये मैपिंग जो है वो नोन है ट्रांसमिटर और रिसीवर. Okay, so SIT, so this is a waveform which is suitable. This is a waveform which is suitable, to be transmitted over channel. Now why have we done this? It means कि इसके अंदर आपका पास बैंड मॉड्यूलेशन भी आ जाएगा. मतलब आपको MI के कॉरस्पॉन्डिंग एक ऐसी SIT बनानी है जो कि आपके रिक्वायरमेंट्स को कन्फर्म करे. जैसे कि आपने बोला कि I am giving you a band of 900 to 910 megahertz. So if there is a message MI and you need to design a waveform SIT which will go from 900 to 910 megahertz, so you have whatever processing you do to do that will all be subsumed in SIT. It means SIT is a perfect waveform as per your demand. So if at all you need to transmit it in some band, so that information also it will take. It means जो आपने मॉड्यूलेट करेंगे, मॉड्यूलेशन के बाद की वेवफॉर्म SIT रिप्रेजेंट करेंगे, क्योंकि हम जनरल थ्योरी बना रहे हैं. इट मींस हम ये कहना चाहते हैं कि SIT वो वेवफॉर्म है जो डायरेक्टली चैनल पे जाएगा. ओके, अब इसके अंदर और कोई फर्दर प्रोसेसिंग नहीं होगी. सो MI, the mapping is now complete. It means there is no further processing on SIT. SIT goes over the channel. Okay. So what is SIT? So let us write something about SIT. So it is a real valued. It is a real value. Real valued why? Because this ultimately goes over the channel and nothing, let us say, complex can go over the channel. So real valued energy signal. It means it has a finite energy. And energy which occupies the full duration T. Now why do you say full duration T? Allotted to symbol. Now it is self-explanatory. MI. It means जितनी ड्यूरेशन आपने MI को है, तो आपने देखा ही है ऊपर सिंबल रेट क्या है हमारा, सिंबल रेट is T. So every T second you will get one symbol. So SIT should exist for T seconds. Okay, so this is quite obvious because this SIT is directly linked to, or it is in conjugation with MI, and MI has a rate of T. It means every T second you get one MI. Okay. So the energy, when we say that it is a real value energy signal, so we need to define the energy as well. So energy definition says that it has to be from 0 to T because this exists only from 0 to T. So SI square T dt. So I am not using absolute value because we have already said that SIT is a real value energy signal. Okay, dt. So for all I 1, 2, up to the possibilities capital M. So we say that this is EI and this is always less than infinity. Why? Because we have defined it in this way. It is a real valued energy signal. Okay. So for developing the theory, this all goes over a channel. And I think we have already studied in the error rate due to noise that the channel standard right now we are considering is the additive white Gaussian noise channel. So channel, what does it do? It adds WT, which is a sample function, which is a sample function of zero mean white Gaussian noise process. it separately so that if you go back and read the notes, it should not lead to any confusion, right? Gaussian noise, random process. Okay. First is this. Secondly, it has sufficient bandwidth which passes the signal without distortion. Okay. It has sufficient bandwidth such that the signal passes without distortion. Okay, it means otherwise हमें Nyquist pulse criteria को भी रोल में लेके चलना पड़ेगा, because it says that if the channel is band limited, it means that whatever you are transmitting, you have to transmit over some particular band, or whatever you are transmitting, it goes through a channel which has a bandwidth which is less than the bandwidth of transmitter, then it will lead to ISI. Okay, so for handling that, you had to design this pulse accordingly. That is Nyquist criteria you had to use. But right now we are studying the effect of noise on the communication system, so we are assuming कि अभी ISI वाला जो distortion है वो नहीं है system में. उसको मानने के लिए what you have to do is you have to say that channel has sufficient bandwidth. It means अगर हम B बैंडविड्थ में ट्रांसमिट करना चाहते हैं तो चैनल की बैंडविड्थ B से ज्यादा ही है, तो कोई बैंड लिमिटेड नेचर नहीं है चैनल में हमारे ट्रांसमिशन के लिए. ओके, सो देन व्हाट, एंड द चैनल इज लीनियर एज वेल, सो चैनल इज, let us write it is instead of channel, so it is linear as well. So linearity is a desired property right now to study systems well. It is linear as well. So you can recall the theory of linear systems from the days you studied signals and systems. Okay. So let us say this is your transmitter. It sends an output SIT and it goes through the channel. Okay. In channel you have X of t, which is equal to SIT plus WT. Okay. Okay, it means this ST exists from 0 to capital T, and this happens for all I. It means whatever I you transmit, this will have this sort of a reception at the receiver. Okay, so with this framework, let us move ahead and study the system. Okay. So what at the receiver, what will happen? I think I have already written it above, but let me write it down more clearly here. So observe the received signal. Observe the received signal X of t for a duration of t seconds, because what is happening is X of t जो भी आप आउटपुट दे रहे हैं 0 से t के बीच में आप ऑब्जर्व कर रहे हैं, उसके बाद नेक्स्ट 0 से t के बीच में एक डिफरेंट SIT ट्रांसमिट हुआ होगा. मींस एक पूरे टाइम के ऊपर तो एक वेवफॉर्म आ रही है, बट आपको उसको चंक्स में एनालाइज करना पड़ेगा. वो चंक्स क्या होंगे? 0 to t सेकंड्स के चंक्स होंगे, बिकॉज t सेकंड्स के लिए इंफॉर्मेशन फिक्स है क्या भेज रहे हैं आप. जो X of t है वो तो वेरी करेगा 0 से t के बीच में बिकॉज ऑफ द SIT and WT, but the information content is fixed from 0 to t. So you have to analyze the received waveform in chunks of t seconds. Okay. So observe the received signal X of t for a duration of t seconds and make the best estimate. Of transmitted signal SIT और MI. ओके, तो दोनों में से किसी का भी अगर आपने बेसिकली आपको I निकालना है, अगर I पता चल गया आपको कि क्या ट्रांसमिट हुआ है, तो वही आपका टास्क है. ओके. अब now let us study it from the perspective of signal space. Okay, perspective of signal space. This will make our task easier. That is, our study will be somewhat easier. So let us say there is a signal space. Okay, So this is called, let me give the short name SS. This is SS, and you have these signals S1T, S2T, and this is, let us say you have SMT. So you have these all signals which belong to some signal space. Okay. Now, so then let us say when SIT goes through the channel WT, adds up, and takes it to a different point in the signal space. Point यहाँ पे क्या होंगे? Basically point is nothing but a signal. बिकॉज सिग्नल स्पेस में जो पॉइंट्स हैं वो सिग्नल्स हैं, जैसे मैट्रिक्स स्पेस में जो पॉइंट्स है वो मैट्रिक्स हैं, ऐसे अगर नंबर स्पेस है तो उसमें जो एलिमेंट्स हैं वो नंबर्स हैं, तो सिग्नल स्पेस में जो एलिमेंट्स होंगे वो सिग्नल्स होंगे। तो अब जैसे S1T में WT ऐड हुआ तो वो उसको YT की तरफ या XT की तरफ लेके गया, वो XT एक कहीं दूर या पास कहीं पे होगा सिग्नल स्पेस के अंदर। ओके, अब ये सबके साथ होगा, यानी S1T भेजे तब भी यही होगा, S2T भेजे तब भी ये होगा, और SMT तक आप किसी को भी भेजेंगे सभी में कोई ना कोई रैंडम वेव फॉर्म ऐड होगी और वो उसको सिग्नल स्पेस में किसी और पॉइंट पे ले जाएगा। इट मींस वी विल से दैट x of t is somewhere in signal space. x of t is somewhere in signal space. अब ये टास्क है, अब आप थोड़ा सा विजुलाइज कर सकते हैं कि अब आपको किसी ने उठा के जैसे आप यू वर सिटिंग ऑन S1T and now somebody just pushed you up randomly in some direction and you landed at some point. Now let us say I am the observer and I didn't know you were pushed in which direction. So you are given with the new location and I have been asked to tell the which location this user was initially. So किस तरीके का ये प्रॉब्लम है, तो आपको देख के लगेगा कि ये बड़ा कॉम्प्लेक्स टाइप का प्रॉब्लम है भी, तो इसीलिए सारा स्ट्रक्चर प्रोबेबिलिस्टिक रहेगा, इसके ऊपर डिटर्मिनिस्टिक नहीं हो सकता इसके अंदर। इसका मतलब है कि जो हमने एरर रेट ड्यू टू नॉइज में स्टडी किया, दैट अगर आप 1 भेज रहे हैं तो ओकेजनली it might happen that the received values are greater than less than lambda, so that you decide in favor of 0. Okay, so इसलिए एवरेज प्रोबेबिलिटी ऑफ एरर, a decision rule is fixed but it cannot take decisions deterministically. It means उसका में कोई ना कोई एरर हो सकती है, कभी वो सही भी ले सकता है, कभी वो फॉल्टी डिसीजन भी ले सकता है। सो उसका पर्सपेक्टिव ये है सारा का सारा। ओके, so let me write it down. So now with the received point, anywhere in space, anywhere in signal space, how to tell the transmitted. Okay, so this is your problem at hand. So we will solve it. We have done it in the case of binary transmission. Okay, so WT being random, the decision making process is statistical in nature. That is, receiver will make occasional errors. तो अगर इस पॉइंट को हमें सिग्नल स्पेस लॉजिक से समझना हो, जो हमने अभी ऊपर डिफाइन किया है, ओके, सो लेट अस सी दिस। सपोज ये सिग्नल स्पेस है आपका, ये पॉइंट, ये पॉइंट, ये पॉइंट, सपोज ये पॉइंट, these are the m points. You know this. I am the observer and one of you is standing at some point. Let us say at this point you are standing. Okay, you can take any one of your batchmate standing here, and some other batchmate comes and pushes him randomly in some direction. Let us say like this. So this user now goes to this point. Now I am the observer. I had closed the eye when you were being pushed. Now I have opened the eye. So I know that there is someone here. And a person asks me, can you tell this person was at which location when you just closed the eyes? Okay. Now I know that possible locations are this, and this. 1, 2, 3, 4, 5, 6. There are 6 possible locations. But मैं ये बोलूँगा क्योंकि ये रैंडम कुछ था, सो मैं देखूंगा कि सबसे नजदीकी पोजीशन कौन सी. इट मींस which position is the most nearest one. So I will find that maybe this is the nearest one. So I will say that there are quite good amount of chance that this person was here. But I may be wrong as well, because the intensity of push can be high enough that this point might also got pushed at this point. Okay. So this might easily happen. So अब आप थोड़ा सा डिटेक्शन लॉजिक भी समझ गए होंगे कि आप रिसीव पॉइंट से सबसे नजदीकी पॉइंट निकालेंगे जो कि ट्रांसमिट होने की चांसेस हैं, और वो ही आप डिसीजन लेंगे. यही पूरी थ्योरी है, यही अल्टीमेट रिजल्ट है. यू विल यूज द मिनिमम डिस्टेंस डिकोडिंग, बट द लॉजिक इज व्हाट वी आर बिल्डिंग. बट दिस इज व्हाट द लॉजिक इज. मतलब इंट्यूटिव भी है कि आप देखेंगे कौन सा सबसे नजदीकी है. ठीक है. So in this case, because your decision is not fixed, it cannot lead to error-free, you can say, detection. So you will define the average probability of symbol error. So what is that? So the average probability of symbol error okay, that is defined as P of E is equal to summation I is equal to 1 to m P of I, that is a priori probability, into probability of making the error. Okay, that is the detected is not equal to m of I, which you say is transmitted, condition that mi is transmitted. Okay, so we will define this. Mi is what is transmitted, m cap is the estimate, estimate produced by the receiver, okay, and P of m cap not equal to mi, condition mi is the conditional error probability given that the IS symbol was sent. I hope things are clear because I have written the definition, but this is the way you will define the average probability of symbol error. Basically, अब एवरेज निकालना है, तो एवरेज का मतलब यह है कि एक बार के रन ऑफ द एक्सपेरिमेंट से तो आपको कुछ नहीं पता चलेगा. मतलब सपोज आपने जीरो से स्टार्ट कीजिए, जैसे यू स्टार्ट फ्रॉम जीरो सेकंड्स, ओके, एंड देन यू मूव. सो टी इज लेट अस से 2 in this case. So then 0 to 2 you analyze, 2 to 4, then 4 to 6, then 6 to 8. So अगर आप 0 से 2 के बीच में सिर्फ एरर नोट करेंगे कि क्या चांस है, उससे एवरेज नहीं है. एवरेज निकालने के लिए आपको लॉन्ग टाइम के लिए आपने एक्सपेरिमेंट रन किया, तो लॉन्ग टाइम के लिए एक्सपेरिमेंट रन करने का मतलब है कि पूरे चांसेस हैं कि हर पॉसिबल एसआईटी ट्रांसमिट होगा. तो वही आपने निकाला कि सपोज एमआई ट्रांसमिट हो रहा है, तो प्रोबेबिलिटी ऑफ एरर क्या है उसकी, वो निकाला. ठीक है, उसको उसके अप्रियरी प्रोबेबिलिटी से मल्टीप्लाई किया और सम कर दिया. Basically, this is what is the average probability of symbol error should be. I am not going into defining it because I feel that this is quite intuitive and straightforward. Otherwise, define कर सकते हैं, event बना के वो सब काम करके भी, पर we will land up at the same answer. And those interested may do it themselves. It means it's easy, not very difficult. Okay. Now, an obvious approach at the receiver. So, what you will do? I think that we have already done for the binary case. So, obvious approach at receiver, which may or may not be optimal, may not be the best, but you can say intuitive approach or an engineer's approach is to minimize this P of E. So, receiver should minimize the average probability of symbol error. This receiver is said to be optimum in the minimum probability of error sense. Minimum probability of error sense. ओके और मिनिमम एवरेज प्रोबेबिलिटी ऑफ एरर सेंस में ऑप्टिमम है, मतलब आपने क्राइटेरिया बताया है तभी आप कह सकते हैं कि ऑप्टिमम है उस सेंस में। ये ग्लोबली ऑप्टिमम है वो कहना अभी इट्स नॉट वेरी इजी, ओके, अनलेस यू डू सम वर्क ऑन इट कि क्या बेस्ट अप्रोच है। बट इंजीनियर्स अप्रोच या क्रिएटिव अप्रोच है कि भाई एरर कम हो, वही चाहिए हमें अल्टीमेटली। तो उस सेंस में हमें ऐसा रिसीवर डिजाइन करना है जो कि इस एवरेज प्रोबेबिलिटी ऑफ एरर को कम करे, ओके। सो अब हम सिग्नल स्पेस की बात कर रहे हैं, तो हम इस स्टडी के लिए क्या अपने काम को आसान कर सकते हैं? कर सकते हैं, क्योंकि हमें पता है देयर इज वन थिंग व्हिच वी नो दैट SIT, S1T, S2T and SMT, they form a subspace. They form a subspace, or they belong to a subspace is better word. They belong, or you can say we can enforce them. That would be a better word. We can model them to be belong to a subspace generated by basis functions phi1t, phi2t and up to, let us say, phi n(t), where the requirement is n should be less than equal to n, okay। अब ये क्या किया हमने, देखो, अगर इफ यू रिमेंबर, आई वुड लाइक टू जस्ट पॉइंट इट आउट हियर, रिमेंबर द GS process, okay, remember the Gram-Schmidt procedure. What it does is it helps you find one-to-one correspondence between the signal and its vector representation, okay। मतलब जो सिग्नल स्पेस का you can say एक बराबर का और बिल्कुल उसके जैसा यूक्लिडियन स्पेस बना देता है। वो यूक्लिडियन स्पेस कैसे बनता है? यू चूज अ सेट ऑफ बेसिस फंक्शंस, वो जो कि वो बेसिस फंक्शन यू कैन डिजाइन फ्रॉम दीज सिग्नल्स इटसेल्फ। अगर आपको S1 से लेके SMT गिवन है, so with the help of these M signals you can define or you can find these capital N signals, okay, that is through the GS procedure। तो आपने ये कहा कि अब देखो क्या है कि हम वही स्पेस let us move ahead and it will be clear to you what we are saying। So आपने S1 से लेके SMT का जो स्पेस, इससे आपने कैपिटल N बेसिस फंक्शंस बनाए। अभी कैपिटल N बेसिस फंक्शंस they can have all possible linear combinations and they can generate signals, okay, and whatever signals they generate, obviously S1 to SMT would be one of them, okay। ऐसा नहीं है कि ये जो N बेसिस फंक्शंस हैं ये सिर्फ कैपिटल M बेसिस सिग्नल जनरेट कर सकते हैं, no, they can generate more than that। So with this as the case कि हमने अब बेसिस बना लिया, क्योंकि हम आसान बनाना चाहते हैं अपनी स्टडी को, तो हम इसको एक सिग्नल को उसके वेक्टर फॉर्म में लिखेंगे तो उससे हमको समझना आसान होगा, ओके। दैट इज व्हाट वी इंटेंड टू डू, अदरवाइज हम अल्टीमेटली प्रोसेसिंग तो सिग्नल के ऊपर ही करने वाले हैं, ओके। सो वी कैन मॉडल देम टू बिलोंग टू सबस्पेस जनरेटेड बाय बेसिस फंक्शंस एंड ईच ऑफ SIT can be written as a linear combination of pi j t's, where j will belong to j is equal to 1 to up to n, Okay, so that is quite obvious. Okay, so first step, okay, let us write it down. Suppose SIT. So for example, let me add for example, what is SIT? SIT can be written as summation Sij by Jt, where J lies from 1 to capital N and T lies from 0 to, okay, and I is equal to 1, 2, 3 up to M. Okay. So we have M, capital M signals and capital N basis functions where N is less than equal to M. This N is less than equal to M. I talked about it when we were discussing the GS procedure. So you can go back and read it. अब ये सब क्यों हो रहा है, ये कहना बहुत जरूरी है. ये सब इसलिए हो रहा है क्योंकि यूक्लिडियन स्पेस में चीजों को समझना हमारे लिए समवट इजी है इंस्टेड ऑफ द कंटिन्यूअस टाइम स्पेस फ्रॉम 0 to t. और ये बिल्कुल यू कैन से 1-to-1 कॉरेस्पॉन्डेंस है दोनों. ये हमने जीएस में देखा है. नहीं तो आप सिग्नल स्पेस का आई हैव गिवन यू रेफरेंस देयर दैट यू कैन गो बैक एंड रीड आई थिंक चैप्टर 1 or 2 of PP Latti's book, quite well written. Okay, I think it is written in the notes. I have given this reference that time. Okay, so अब ये कैसे, अब सबसे पहले क्या करेंगे, अब आप xt है, so what we will do is, okay, now you receive xt, so at the receiver, let us write down that at the receiver, you have x of t and you know 5 jt's for j, ये आपको पता है. अब सबसे पहले आप जानते हैं व्हाट इज द सिग्नल सबस्पेस. लेट द सिग्नल सबस्पेस generated by 5 jt's be called v. Okay, अब आपको पता है कि आप जैसे से ये पूरा सिग्नल स्पेस है. ओके, दिस इज योर सिग्नल स्पेस and there is a small, you can say, subspace that is called as V. So all your points, they belong to this subspace. Now you will receive some point which is in the signal space. So x of t can belong anywhere in SS. X of t can be anywhere in SS. Okay, but हमें किससे मतलब है, हमें तो V से मतलब है. तो obvious strategy is to project xt on V. Okay, so why not, let me write, because we transmit points only from V, let me write it in that manner, as we are transmitting only from V, why not we project x of t on V and then do the detection. ओके, मीन्स कि क्या पॉसिबल, हम एक्स टी का जो कंपोनेंट है V, मतलब V ने क्या कंट्रीब्यूट किया है एक्स टी में, अगर वो पता चल जाए आपको तो हम उसके ऊपर डिटेक्शन करेंगे तो वो ऑब्वियस अप्रोच होगा. मीन्स एक्स टी जो है इट कैन बी रिटन एज कंट्रीब्यूशन फ्रॉम V प्लस कंट्रीब्यूशन फ्रॉम समथिंग आउटसाइड. तो हमें इस आउटसाइड कंपोनेंट का कोई यूज नहीं है. व्हाट शुड वी डू ऑफ दिस? ओके, सो वी कैन रिमूव इट और वी कैन जस्ट ओनली गेट दिस कंट्रीब्यूशन फ्रॉम V बाय प्रोजेक्टिंग xt on V. In order to do so, what do we do is that we will apply x of t and we will project it on each of the basis functions. How do you do it? Simply do the correlation. Okay, This goes on, finally this goes to phi nt. This is the integration device. This is the way you do the projection in the signal space, or this is nothing but the dot product. Okay, ये dot product है. अगर आप इसका एक analogous operation impedance space में ढूंढेंगे तो this is nothing but dot product. This you will easily find in lattice chapter 2. I have given the reference when we were discussing the GS procedure. So we will find some components. Let us say I call it x1. This is x2. This is your x of n. Okay. So you get a vector. So for corresponding to its projection on V gives you a vector x of bar. Okay. बेसिकली सिग्नल आएगा और उसका जो कॉरस्पॉन्डिंग रिप्रेजेंटेशन है वो x ऑफ बार है. ठीक है, मतलब ये जो x ऑफ बार है इज नथिंग बट लेट अस से द प्रोजेक्शन इज कॉल्ड इज x प्राइम t. लेट मी राइट इट डाउन. Let me be more very specific so that those who go back and read through notes, they should not get confused. So I will let x prime t be its projection on V, where x prime t is nothing but summation x of, you can say, j by j t. J is equal to 1 to capital N. So what I am saying is that I get this vector x bar which is equal to collection of all these x1, x2 up to x of n transpose. So this is what I wanted to say when I wrote those lines earlier. So x prime t वो सिग्नल है जो कि x of t की प्रोजेक्शन है ऑन v से, मतलब v का टोटल कंट्रीब्यूशन x of t में कितना है, और कायदे से v में ही हमने जो सिग्नल है वो भेजा है, मतलब s1t बिलोंग्स टू v. सो हम ही जानना चाहते हैं. ओके, अब हम स्पेसिफिकली इसकी इक्वेशंस वी कैन राइट डाउन. सो x of j is nothing but integral 0 to t x of t phi j t of t. Okay, which can be written as, let us say, what is x of t? That is some SIT. If you assume that you transmitted SIT into phi j dt, which is equal to nothing but Sij. Okay, now sorry, this is 0 to t plus straightforward analysis, and this is nothing but Sij. I think I have not defined it earlier. I just written that this is what it is. Once you go back and read the GS procedure, you can easily find out that this is the definition of Sij. And plus, let us write this then as Wj. Okay, where Wj is this integral. That is, this is Wj, and this is your x of j. Okay. Now, what is x of t? Now, can I write x of t as this? X of t can now be written as, x of t was this. Okay. Now, can I write this as like this? Sit plus summation j is equal to 1 to capital N Wj by jt plus Wt minus summation Wj. I can write it because okay. So now x of t, and now the Sit I know is nothing but Sij phi jt, j is equal to 1 to capital N plus Nwj So let us call this a WET. Okay, this is nothing but WET. So this can be written as what? This is nothing but if you combine in Sij Wj into phi jt WET. This is nothing but, you know what is this? We have defined already. This is x of j. This is the way we can define it. This is your x of t. So this is what? This is the contribution from the space v, okay, into x of t. क्योंकि ये जो वेक्टर होगा समेशन ऑफ j 1 से लेकर n तक xj phi jt would be somewhere in v. So ये वो वेक्टर, let us say this is this point, you add some point to it and you land up at this point. So now you have just somehow find out that in v what is the component of x of t. Okay. Now what do we call it as? This is called as the, I think I have already mentioned this, but let me write it down again. This component says projection of x of t on the signal subspace V. Okay. Now let us do some characterization. अब सबसे बड़ी बात ये है कि हमें क्या पता था, SIT for all I are deterministic and WT is a Gaussian random process. Okay, so x of t will also be a random process. But what about this? Whether it will be Gaussian or what sort of a random process? Random process तो होगा क्योंकि SIT deterministic waveform है और मतलब for all I, जैसे से आपने S2T भेजा, S2T में आपने एक रैंडम फंक्शन, रैंडम सैंपल फंक्शन WT ऐड कर दिया, तो जो आपको x of t मिला, अगर मैं x of t इन जनरल बात करूं कि आज मुझे क्या x of t मिलेगा, थोड़ी देर बाद मुझे क्या x of t मिलेगा, कल मुझे क्या x of t मिलेगा, ये सब एक रैंडम प्रोसेस है क्योंकि हर दिन एक अलग, इवन अगर मैं SIT को फिक्स कर दूं कि S1T ही भेजूंगा मैं रोज सुबह, लेट अस से t2 सेकंड्स का इंटरवल है, तो मैं कहता हूं मैं सुबह 9 बजे भेजूंगा, दिन में 12 बजे भेजूंगा और शाम को 6 बजे भेजूंगा, तो 2 सेकंड का इंटरवल है, मतलब 9 से लेके 9:02 तक भेजूंगा, 12 से लेके 12:02 सेकंड, 2 मिनट तक मीन से व्हाटएवर, ओके, एंड 5 से लेके मैं 5.2 तक भेजूंगा और मैं S1T ही भेजूंगा. सो जो x of t मुझे अब मिलेगा, जो x of t मुझे यहाँ मिलेगा, जो x of t मुझे यहाँ मिलेगा, वो सब अलग अलग मिलेंगे और ये चीज हर दिन अलग अलग होगी. तो इसका मतलब ये है कि इवन अगर x1t को फिक्स किया जाए तो x of t अलग अलग चीज मिलेगी, मतलब x of t एक रैंडम प्रोसेस होगा. इतना तो मैं श्योरिटी से कह सकता हूँ. इट इज क्वाइट स्ट्रेट फॉरवर्ड. आई एम एडिंग अ डिटरमिनिस्टिक वेवफॉर्म टू अ रैंडम वेवफॉर्म, सो द रिजल्ट वुड बी रैंडम. दैट इज क्वाइट ऑब्वियस. Now the problem is, can we characterize whether it will be Gaussian or what sort of distribution it will follow, और जो इसके सैंपल वैल्यूज होंगे वो किस तरीके के रैंडम वेरिएबल होंगे? तो आंसर है कि यस. सबसे पहले हम यही काम करेंगे. ओके, सो फर्स्ट वी विल रिवाइज वन थिंग, स्मॉल थिंग, दैट we know that if the input to linear system is a Gaussian random process, the system output is also a Gaussian random process. This I have quoted without proof. I think 3-4 lectures before I just quoted this without proof. Today I am not proving it, I am just stating it and just explaining why it happens. Okay, so this is because This is because we should know this. Any set of output samples can be expressed as a linear combination of input samples or the limit of such linear combinations. I would suggest that if you can read these lines, those who are attending, they are very important and integral for computing. For example, a convolution is the limit of a sum. Is the limit of a sum. Okay. So what we are saying is that ये तो फैक्ट है ये कि लीनियर सिस्टम के अंदर अगर आपने इनपुट डाला है गॉसियन रैंडम प्रोसेस, सो जो आउटपुट आएगा वो भी गॉसियन रैंडम प्रोसेस होगा. अब हम जानते हैं कि लीनियर सिस्टम को हम एक इंपल्स रिस्पॉन्स से भी रिप्रेजेंट कर सकते हैं और आउटपुट को हम कॉन्वोल्यूशन ऑफ इनपुट विद द इंपल्स रिस्पॉन्स के रूप में रिप्रेजेंट कर सकते हैं. बट कोरिलेशन भी जो हमने देखा है कि कोरिलेशन कैन आल्सो बी इंप्लीमेंटेड थ्रू अ फिल्टरिंग ऑपरेशन. You can have a filter with an impulse response which is, let us say, TB minus T or minus T of the waveform through which you want to correlate, and then sample the output at T. So it means that correlation obviously is a linear operation. You can clearly see it is simply multiplication of the two signals and integration from 0 to some limit or y is infinity to infinity. So that being a linear operation, so if at all I am correlating a Gaussian random process with some waveform, output would also be a Gaussian random process. The reason is because any set of output samples can be expressed as a linear combination of the input samples. Quite obvious, because or the limit of such linear combination. देखो इंटीग्रल क्या है? इंटीग्रल भी लिमिट ऑफ सच लीनियर कॉम्बिनेशन ही है. आप छोटे छोटे बिट कर देते हैं this variable of integration के, you can say t is the variable of integration. So you take delta t bits of the time axis, you multiply it with the value that the functions take in that limit, and you sum. So this is the sum over infinitesimally, you can say values which are very very close, the values which are at infinitesimal distance from each other. So integral is nothing but the limit of such sum. So अब ये तो GRP की definition थी कि Gaussian random process क्या है कि for any t1 t2 up to t of n, if I collect the random variables, their linear combination should lead to a Gaussian random variable. So अगर GRP है तो ये हो गई होगा. तो जब आउटपुट आया सिस्टम का वो एक लीनियर कॉम्बिनेशन आया इनपुट सैंपल्स का. सो ऑब्वियसली बात है वो तो गॉसियन हो गई क्योंकि वो तो गॉसियन रैंडम प्रोसेस की डेफिनेशन थी जो इनपुट पे था. तो आउटपुट वाला भी एक जीआरपी ही होगा. ओके, सो दिस इज व्हाट इज दिस. ओके, okay, so let us now move ahead. So from this explanation, we can say that x of j is a Gaussian random variable. Is a Gaussian random variable. How? Because x of j is nothing but correlation of x of t. So आपने क्या किया, ये एक गॉसियन रैंडम प्रोसेस है, अभी हमने बोला नहीं है इसको, but let me I will tell you. So this is a Gaussian random process and you are now correlating it with phi j_t. So this is a linear system and you are collecting the output. Now output will be a num value, okay, because this is correlation. This is not filtering. Filtering gives you a time function. So if you sample that time function, you will get this value. So this becomes a random variable. So output जो है Gaussian process है random, उसका आपने sampling कर दिया तो x of j. So x of j will be a Gaussian random variable. Okay. So we have not yet said that how come your x of t. So x of t was what? Is some SIT plus WT. Now this is a Gaussian random process. Now the question is, will this also be a Gaussian random process? That is the question. Okay. Now yes, it should be. How? Let us check this out. Okay. So x of, let us see this. So this being GRP, WT being GRP, we know that for any T1, T2 up to some T of P, W of T1, W of T2 up to W of TP are jointly Gaussian. ये हमें पता है. Meaning summation of some alpha I WTI P, whatever you get is a Gaussian random variable. Okay. Now let us check this. What about x of t1, x of t2 up to x of tp? So ये क्या है? si of t1 plus w of t1. ये क्या है? si of t2 plus w of t2. Now ये सब deterministic है. They are constant, okay? Or you can say deterministic. That's constant. They are nothing random, okay? Now अब ये जो एक वो है, if WT1 is a Gaussian random variable, then SIT1 if you add, so let us say this is a Gaussian random variable and you are adding some constant to it, so the output would also be a Gaussian random variable with a different mean, okay? So mean क्या बन जाएगा? SIT1. Okay. So what is happening is that अब आप इसको सम कीजिए arbitrary, जैसे अल्फा I SI, sorry, it should not be alpha I should take it to K. It's better if I take it as K because I have already used. This should be some K. So you take it as K. So it's alpha of K, SI of TK plus WTK. And you are finding k is equal to 1 to p. So you are finding if at all this would be a Gaussian random variable or not. Let us see it. How can I write it? You will see the beauty, okay? Alpha I SI T K plus summation k is equal to 1 to p alpha k W of tk. Now we know that this is a Gaussian random variable because W of t is a Gaussian random process. Now this is a GRB and this is a constant. This sum is a constant. So we have studied that if the case is y is equal to a plus x, where this is a Gaussian random variable, then this is also GRB with the mean of x being shifted, or you can say added, shifted by a. So hence proved, it means that x of t would be a Gaussian random process. Okay. तो दिस इज अ वेरी वेरी यू कैन से, ये तो कहना तो आसान है कि कोई भी कह दे कि ठीक है भाई WT ऐड हुआ है XIT में तो X ऑफ T एक गॉसियन रैंडम प्रोसेस है। कैसे होगा? अगर आप डेफिनेशन से बताना चाहेंगे तो फिर नहीं कर पाएंगे। तो ये इसका एक सिंपल मैंने आई हैव जस्ट गिवन यू द वे यू सी दिस। So this clarifies this that xj would be a Gaussian random variable. Okay. So let us obtain the mean and variance of so today we will just obtain the mean and variance and then we can close for the day. So what is mean of xj? This is nothing but expected value of x of j, which is equal to expected value of Sij plus Wj, which is equal to Sij. Why? Because expected value of Wj is 0. Wj is nothing but, so okay, we have not yet said anything about Wj, so we'll do it in the next class. So this is equal to expected value of x of j minus Sij whole square, and this is equal to expected value of Wj whole square. Okay. So I think we can close at this point for today. We have just obtained the mean and variance. I will just elaborate on it finally in the next class, and in the next class we will just close up with the theory of detection, and then from Tuesday, that is next Tuesday or the coming Tuesday, the 3 lectures which we have, we will just invest on the 3 modulation schemes, that is BPSK, QPSK and QAM. With whatever base we have built, it won't take that much time to study those schemes, okay, because we have now built the base for signal space. We now know the detection, we now know pulse shaping, we now know the power spectral density, everything we know. So it's just a task of merely 2 to 3 hours to study those schemes. That is what I assume. Okay, so we are done for the day. So those who want to stay to talk on something, they can, otherwise you can leave.